Hello and welcome to Equations. My name is Neil. I'm a mathematician and a math educator. In my video series, I try to teach mathematics in a way that is not usually taught in school. I hope that I will be able to show you the beauty of the subject and inspire you to fall in love with it. In this video, I'm going to teach you an interesting trick. If I give you only one side of a right triangle, can you find the two missing sides? The only information that you have is all the sides of the right triangle are integers. This problem is different from the problems that we usually learn in school, where we are given two sides of the right triangle and we are asked to find the third missing side. If we are given two sides, then the problem is pretty straightforward. We use the Pythagoras equation. We are given two sides, so we can easily find the missing side. However, when you are given only one side, the problem is kind of interesting and challenging, at least at school level. So let us solve this problem first. I will show you with a working example, and then later in the video, I will explain the solution to you in details. Suppose that we are told that one of the side of the right triangle is 2019. Can we find the other two sides if no other information is given? The only information that we have is all the sides of the right triangle are positive integers. So with this bare minimum information, we need to find the missing side. Since we do not know if the missing side is the hypotenuse or one of the two perpendicular sides, so we cannot straight away assume that it is the hypotenuse or not. So let us consider both this scenario. In the first scenario, we assume that the missing side is the hypotenuse, and let us say that the other two sides are a and b. Then we will have a square plus b square. This is equal to 2019 square. In the second scenario, we assume that 2019 is not the hypotenuse but one of the two perpendicular sides. So in this case, the Pythagorean equation will be a square plus 2019 square. This is equal to c square. Let me show you the solution for the first case, and later in the video when I explain the method to you, you will be able to solve this question for the second case as well. 2019. So 2019 can be factorized as 3 times 673. What I will do next is I'm going to express 673 as the sum of two squares. 673 is a prime number and it can be written as the sum of two squares. This is equal to 3 into 23 square plus 12 square. 23 square plus 12 square is equal to 673. So I denote 23 by the letter R and I denote 12 by the letter S. So my R and S are 23 and 12 respectively. Since I'm solving the first case where 2019 is the hypotenuse, so I will have a square plus b square. This is equal to 2019 square, and my a will be given by 3 times r square minus s square. This is equal to 3 times 23 square minus 12 square. This is equal to 1155. b will be given by 3 times 2 times r times s. This is equal to 3 times 2 times 23 times 12. This is equal to 1656. And finally, c will be given by 3 times r square plus s square, which we already know that this is equal to 2019. Thus we have 1155 square plus 1656 square. This is equal to 2019 square. So you see, just by using simple mental arithmetic, we are able to find a right triangle where 2019 is one of the sides of the triangle. So let us consider a right triangle A, B, and C where A and B are the two perpendicular sides and C is the hypotenuse. Then the Pythagoras theorem says that a square plus b square is equal to the square of the hypotenuse. In fact, this particular theorem is one of the earliest that was known to the humankind. It dates way back to 1800 BC, first discovered in, I think, Babylon. But it would be wrong to say that, because more or less every civilization independently discovered the Pythagorean theorem. India, Egypt, China, Greece, everywhere. Somehow the name of Pythagoras stuck to it, because it's been a convention for the last 500 years to name almost every ancient scientific discovery after a Greek philosopher. So no difference and no exception to the Pythagoras theorem. We're going to name it after Mr. Pythagoras, who was not an ancient mathematician but a philosopher. Nonetheless, he gets the credit, even though we don't know who the original discoverer of the Pythagorean theorem was. Let's look at a few examples of Pythagorean triplet. 3, 4, and 5 is the simplest, the smallest, and the most popular Pythagorean triplet. Next we have 6 squared plus 8 squared. This is equal to 10 squared. Another example would be 7 squared plus 24 squared. This is equal to 25 squares. So square plus 12 squared. This is equal to 13 squared. Another example would be 9 squared plus 12 squared. This is equal to 15 squared. Let us look at the greatest common divisor of this Pythagorean triplet. For example, 11, 60, and 61, they have no common factor. The greatest common divisor is 1. Similarly, the greatest common divisor of the first Pythagorean triplet, 3, 4, 5, is equal to 1. That of 6, 8, and 10 is equal to 2, because all these numbers are divisible by 2. The GCD of 7, 24, and 25 is equal to 1, because we do not have a number greater than 1 which divides all of these numbers. Likewise, that of 5, 12, and 13, the greatest common divisor of this three number will be equal to 1. There's a reason why we are looking at the greatest common divisor, as you shall see in the subsequent discussion how we are going to use the property of greatest common divisor. So let's look at the last one. 11, 60, and 61, they have no common factor. Therefore, the greatest common divisor, GCD, of this three number is equal to 1. So now we can classify the Pythagorean triplets into two types. The triplets for whom the GCD is equal to 1, we call them as primitive Pythagorean triplets. So the definition of a primitive Pythagorean triplets are the triplets which have no common factor. Similarly, the triplet for which the greatest common divisor is greater than 1, we call them a non-primitive Pythagorean triplet. Consider the primitive Pythagorean triplet 3 squared plus 4 squared equal to 5 squared. If you multiply each of these numbers by, let us say, 2, 6 squared plus 8 squared, this is equal to 10 squared. Similarly, if we multiply each of the original number by 3, we get 9 squared plus 12 squared, this is equal to 15 squared, which is another new Pythagorean triplet. In general, we can multiply by a constant, say k, and we will be getting 3k squared plus 4k squared, this is equal to 5k squared, where k can be any positive integer greater than or equal to 1. So all of this are derived from the primary triplet 3, 4, and 5. So these derived triplets are the non-primitive Pythagorean triplet, and they're all derived from the primitive triplet, which is 3, 4, and 5. Now, if we look at the GCD of any derived primitive Pythagorean triplet, obviously it will be greater than 1. In general, the GCD of 3k, 4k, and 5k will always be equal to k. So using this method, we can now cheat the system somewhat and generate infinitely many Pythagorean triplets. Suppose we are given a right triangle, say the hypotenuse is 37 and one of the sides is 35. We are asked to find the missing side. We can solve it very easily using the Pythagorean equation. Let's say the missing side is x. Then we have 37 squared is equal to 35 squared plus x squared. Transferring x to the left-hand side, we have x is equal to 37 squared minus 35 squared, and we take it under the square root sign. And this gives us x is equal to 12. So you see it's extremely easy when you are already given two sides. More or less there's nothing to compute. You only have to take the square root of the difference and that gives us the answer. But what about the situation when you have only one side of the right triangle and you are asked to find the other two sides? How would you solve that? That is something that I want to focus on this video, and this is a method that is not taught in schools. Now we come to the most interesting part of the tutorial. What if we are given only one side of a right triangle? Let us say 41. We don't even know if 41 is the hypotenuse or one of the perpendicular side. So we need to consider both this option. Option 1, let us assume 41 is the hypotenuse. 41 is the hypotenuse and the other two sides are x and y. So we have x squared plus y squared must be equal to 41 squared. This is a possibility. The second option or possibility is we assume that 41 is one of the two perpendicular sides. So we draw the triangle here and let 41 be one of the two perpendicular side. The other unknown side be y and the hypotenuse be z. Then we have 41 squared plus y squared. This is equal to z squared. We need to consider both the situation. So we'll solve it twice, once for 41 being the hypotenuse and the second time for 41 being one of the two perpendicular or orthogonal side. So in this example, what I'm trying to show you is that a number can belong to multiple Pythagorean triplet. Let us look into the solution. We'll first look into the solution using an example, the example of 41, and then after that I will explain why the solution works. The first step of the solution is to express 41 as the difference of two squares. So we'll try to write 41 as 41 equal to r square minus s square, where r and s are two positive integers. If we can find such integers, then we're done. So 41 can be written as 1 into 41, which can be written as 21 minus 20 times 21 plus 20, and this is equal to 21 square minus 20 square. So we have written 41 as the difference of two squares. So our r is equal to 21 and our s is equal to 20. So using this r and s, we will find all the sides of the right triangle. The first side of the right triangle, one of the two orthogonal sides, is a equal to r square minus s square, which we know to be 41. The second perpendicular side or orthogonal side is twice rs. This is equal to 2 times 21 times 20 is equal to 840. And the third side or the hypotenuse is r square plus s square. This is equal to 21 square plus 20 square is equal to 841. So our complete solution in this case is 41 square plus 840 square. This is equal to 841. So by expressing 41 as the difference of two squares, we are able to find a solution for the Pythagorean triplet. Let us look at the second solution involving the number 41. In this solution, we will try to write 41 as the sum of two squares, r square plus s square. Once we get r and s, we will get our solution. So let's try. 41, it can be written as 1 square plus 40. But 40 is not a square. So we try again. 2 square plus 37. But 37 is not a square. 3 square plus 32. 32 is not a square. 4 square plus 25. Hold on. 25 is a square. So 41 is nothing but 4 square plus 5 square. So using this information, our r is equal to 5 and our s is equal to 4. This is because r is always greater than s. So the next step is we get our solution, we are done. So a will be equal to r square minus s square. This will be equal to 5 square minus 4 square, and this is equal to 9. B will be as usual twice rs. This is equal to 2 times 4 times 5, this is equal to 40, and c will be r squared plus s squared, which we know to be equal to 41. So our complete solution in this particular case is 9 squared plus 40 squared. This is equal to 41 squared. This is the second solution that we got using the number 41. In the previous case, we got 41 squared plus 840 squared equal to 841 squared. So overall, we have two solutions involving the number 41. So with these two examples, I have shown you how to find a solution when only one side of a right triangle is given. Now, let us look at the general solution and understand why this particular methods work. So suppose that we have a number a which can be written as r squared minus s squared, and b which can be written as twice rs, and c which can be written as r squared plus s squared. A is the difference of two squares, b is twice rs, and c is the sum of two squares, r squared plus s squared. If you have three numbers, then what you can do is you take the square of a, which is the square of r squared minus s squared, add it to it the square of b, which is twice rs squared, and this will be exactly equal to r plus s the whole square. So we have broken down the Pythagorean triplet into its component. This is exactly what the general solution of a Pythagorean triplet looks like. All Pythagorean triplet can be broken down into this format. So if we are given one side, the first thing we need to do is check if the one given side n can be written as the difference of two squares. Number two, check if n can be written in the form twice rs. And number three, check if n can be written as the sum of two squares, r squared plus s squared. If any of these three or more than one of these three options is possible, then we have a solution. So if we have broken down n into its component r and s, then a right triangle will have twice rs as one of the perpendicular side, r squared minus s squared as the other perpendicular side, and r squared plus s squared as the hypotenuse. Let us solve one more example to understand our solution better. Until now, we have used the number 41 and got two solutions, both of which are primitive. Now let us look at a non-primitive solution. Suppose one of the side is 70. Can we find the other two sides of this right triangle? So notice that 70 is an even number. So our starting strategy would be slightly different. Instead of trying to write 70 as the sum or difference of two squares, we first factorize 70. This is equal to 2 times 35, which is equal to 2 times 5 into 7. Remember that we had a format where we wanted to express the given number n as 2 times r into s. 70 fits this format perfectly. 70 is equal to 2 times 5 into 7. So our r is equal to 7 and our s is equal to 5. Therefore, a, or one of the perpendicular side, this will be equal to r squared minus s squared, which is equal to 7 squared minus 5 squared. And this we can easily compute it to be equal to 49 minus 25, and this is equal to 24. So one of the perpendicular side is 24. The other side would be twice rs, which we already know that is equal to 2 times 5 into 7. This is equal to 70. So we have already obtained two sides. The third side would be r squared plus s squared. This is equal to 7 squared plus 5 squared, which is equal to 49 plus 25, and this is equal to 74. So we have obtained all the three sides of the right triangle by observing the simple fact that 70 can be factorized as 2 times 5 times 7. So this is our solution using our first method of splitting our given number as 2 times r into s. So we obtained our first solution as 70 square plus 24 square. This is equal to 74 square. If you observe carefully, each of this number 70, 24 and 74 are all even number and they are all divisible by 2. Therefore, this is a non-primitive triplet. In order to get the original triplet, what we can do is we can divide each of them by 2 to get 35 square plus 12 square. This is equal to 37 square. So this particular triplet, which is derived from 35, 12 and 37, is our non-primitive triplet. Now let us look at more solutions that involve the number 70. In the first solution, we express 70 as twice rs. Now let us express 70 in a different format. Let's say 70 is equal to 2 times 5 into 7. This is equal to 14 times 5. And 5 can be written as the sum of two squares. 2 square plus 1 square into 14. So we have now expressed 70 as a constant k, remember, and the sum of two squares. So we are into the case of non-primitive Pythagorean triplets. So now, what will our first perpendicular side be? A will be equal to 14 times r square minus s square. This is equal to 14 times 2 square minus 1 square. This is equal to 14 times 3, which is equal to 42. B will be 14 times twice rs. This is equal to 14 times 2 into 2 into 1. This is equal to 14 times 4, which is equal to 56. And finally, C will be 14 times r square plus s square. This is equal to 14 times 2 square plus 1 square. This is equal to 70. So we have obtained one more solution, which is 42 square plus 56 square. This is equal to 70 square. In part 2 of the same series, I will show you many more fascinating properties of Pythagorean triplets. For example, did you know that in a right triangle with integer sides, one of the three sides is always divisible by 3. One of the three sides is always divisible by 4. One of the three sides is always divisible by 5. These and many more interesting properties of Pythagorean triplets will be covered in the next video. So if you like what you are learning, do not forget to like, comment and subscribe this channel. Thank you.